Okay, so light, are you confused yet? Are you feeling pretty confident that you understand it so far? Well, either way, it's okay. If you're confused, you are in good company. People like Albert Einstein and Isaac Newton were very confused by it and spent a lot of their life trying to figure out how to even explain it in the barest sense. So don't feel bad, right? It's something that just takes a long time to figure out. If you don't feel confused, hopefully it's because you've spent so much time trying to think about what waves are and you feel like you can understand the evidence for that double slit experiment at least. In any case, what we're going to be talking about now is a much more simple way of looking at light. It's not saying what is it, it's more of what does it do, right? So interactions of light are going to talk about, well, how does light actually interact with matter, right? How does it interact with other light even? We know that waves are able to be disturbed, right? There's a bunch of different interactions that we know that waves can do when they either contact a boundary or contact matter or contact each other. And that's what we're going to be talking about here. So if you don't already, please have your notes out on light interactions. We're going to be going through here, and then I'm going to give you some time at the end to do a graphic organizer just to check to make sure you understand what these interactions look like and how do we describe them. So all waves can be deflected, changed, but we're going to go through one at a time with absorption being the first one. So absorption, when we say absorb, we write it with a B. When we're saying absorption, we write it with a P. Same thing, different spelling. Thanks a lot, English. So this occurs when light waves transfer energy into particles of matter. When you use a sponge to absorb something, it sucks it up, right? And it stays inside of it. The same kind of thing happens with energy all the time. Thermal energy might be absorbed by something. If you're feeling warm, you are literally absorbing the thermal energy of the sun that transfers to you through radiant energy. You can imagine on a hot day, you feel like the earth is absorbing a lot more of the energy from the sun's light because there's just more sunlight. And then it re-emits it as thermal energy. So if you could look at a diagram of this, think about light coming in and hitting something, and then all of a sudden its energy gets fizzled out inside of that thing. And it could end up causing thermal energy or other types of energy to happen, but mostly it gets transformed into thermal energy. So in the case of a banana, we say that white light has all the types of light present in it, right? We talked about the spectrum of visible light as being Roy G. Biv, red, orange, yellow, green, indigo, blue, violet, which is just, Roy G. Biv is an easy way of remembering the different names of colors of light, but it's not that important, right? You should know that the sun puts out all sorts of light, stuff we can't see, invisible UV rays, infrared, but mostly visible to us, right? And the visible part has red light, orange light, yellow light, green light, blue, indigo, and violet. However, a lot of stuff we see doesn't have all that kind of light. And even the things that we do see that has all that light, we don't see the different parts of it. We just see white. So whoever lied to you back in the day, you can blame them for this. White is not a color, and black is not a color. White is actually all the colors combined. You just can't tell the difference between the whole color of the rainbow and what we would think about as white, right? It just appears to your eyes as white. Counter that, if you saw nothing at all, it would look black, which means that all the light is either not present or it's being absorbed by the thing that you're looking at. So we're going to run a couple thoughts here. Why are bananas yellow then? Think about that. Are bananas absorbing all types of light except for yellow, or are they absorbing only yellow? And the quick check is, do you see the banana? If so, there must be yellow light coming off the banana, right? If you see yellow coming off the banana, then there must be yellow light coming off of it. So let's backtrack then. Where does that yellow light come from? Is the banana glowing yellow? Is it producing its own yellow light? And it's like, obviously not, right? So think about that. Is it a light that's in the room or the sunlight that's bouncing off the yellow banana? Okay, that makes more sense. So Say there's white light present in the room. Is there anything in your room right now that is white? If so, there must be all forms of light present, right? Otherwise you wouldn't see it as white, you just see it as those different colors. So basically, absorption and reflection work hand in hand, right? Whatever's absorbed by the thing, we don't see. Whatever's reflected is what we do see. So in the case of bananas, bananas absorb all the different types of colors of light except for yellow, which they reflect back to you. I guess bananas also reflect green light, right? But then as they ripen, they reflect yellow light. Kind of like maple leaves, not ripening, but they're green at first during the summer and spring, and then as fall comes, they turn yellow, orange, and red. Interesting, right? So absorption is when incoming light hits an object and causes its atoms to vibrate. Those vibrating atoms can usually turn into thermal energy. Sometimes they can get turned into electrical energy, like in the case of a solar panel, through a chemical process. And here's another question for you. So just to make sure you understand this, why do you feel warmer when you wear a black shirt versus wearing a white shirt on a sunny day? Go ask your people in the house right now, or in your apartment. What do they know? Can they explain it using absorption? Okay, so just a quick check here. If you said that the black shirt absorbs all wavelengths of light, meaning that you actually don't see it, right? The same thing would happen. If I turned off all the light, right, you would not see that person's shirt. It would be black. But the fact that you can see the rest of them tells you there must be other forms of light present too, right? So there's only one explanation. The shirt is absorbing all the colors of light. And it has to do something with that energy. It just turns into heat. Well, as opposed to this cool dude over here, right? He's wearing a white shirt. He's smart. All that light's going to reflect off of his shirt and back into your eyes. So this is why you can see it, right? Or back every direction. So if it's reflecting the light, it's not absorbing it, and therefore it's not heating you up. So go wear a white shirt on a hot day, a hot sunny day, right? It is the heat of the day itself. The whiteness or the blackness of the fabric has no difference. It's if you're in the sun, because it's going to either absorb or reflect that light. Okay, so a little bit more of a definition or a fleshing out of this idea of what absorption is. When light hits a non-reflecting surface, the light waves are absorbed by the object. However, the light waves that are the same color as the object are not absorbed. Instead, those light waves bounce off the surface, are transmitted to the human eye, and are basically interpreted by the brain of the person based on the object. I'm sorry, it's cut off there. So in other words, why do you see yellow for bananas? It's because they're absorbing everything but yellow light. Why does an apple look red? It's absorbing everything except for red light. So that's what absorption is. And just think of it like a sponge, right? You see whatever doesn't get sucked up. Just like if you pass the sponge across a table of water, right? Think of the remnants of the water there as being what you see, and those being color normally, right? But whatever's sucked up into the sponge is turned into thermal energy, heat. So transmission is the next thing that can happen when light hits a matter, an object or matter, right? So when light travels through or passes through an object without interacting with it, without absorbing or reflecting, we call this transmission. Now, it never really happens that anything's fully transmitted, but imagine the light goes through, it doesn't get bent, it doesn't change direction, it doesn't get sucked up, it doesn't get bounced right back off the surface of it. This is what we call transmission. Usually glass might have anything from 89% transmission down to, like 0 if it has mirrors on one side of it, right? And glass is just a mirror. So in terms of transmission, we can think about it in terms of transmitting all light, some light, or no light. So imagine this is a red filter right here, or a piece of red glass. If there's all sorts of light coming through on the one side, but on your side of it you only see red, it means it must be absorbing all the light except for red, but the red's still going through it, so we're not just going to say there's nothing happening to it. It is transmitting through the object. Some objects do not allow any light to pass through. We call those opaque objects, like a hand or a book, right? They don't allow light to go through from the other side. We can't see the light through them. So regardless of what's happening, it is just it's opaque. It's not allowing any light to transmit. Some things do allow light to transmit, but not all of it, like sunglasses, right? They allow some of the light to come through, but not all of it, a very little amount of it. You might be able to see the other side of a leaf, or some even creatures are translucent. This is the word for when something's transmitting some, but not all the light. Transparent would be if you can see all the light through something, right? There's very little interaction, very little absorption or reflection. Just once again, transparent would be everything's coming through, translucent a little bit, but not nothing, and opaque is nothing is going through that object. So take a second to think about, how do sunglasses work? You can turn and talk with people in your family if you want, or if they are tired of talking to you, talk to yourself about this. Explain it. How does that work? We're going to go on to the next one now. Refraction. Refraction, we're probably going to hopefully finish it up on this one, if not in the next video. So refraction is the change in direction of a wave, light in this case, when it changes speed as it travels from one material or medium to another. You've all seen this before. You put a straw, or if you don't have a straw in your house, go get a glass, something that's transparent so you can see into it, and put a pencil into it. Watch as it looks like it's coming from one spot, and then it looks like it's broken. And take it back out again. It's not broken. Like, no duh, right? But why the heck does it look like it is? And this is a curious interaction called refraction. When light travels through nothing at all, it's happy, right? It doesn't have to travel through stuff, so why would it want to? It travels very fast through nothing at all. The more dense the medium is that it travels through, like air or liquids like water or whatever liquid this is, the more it's going to slow down. Just like you would slow down more if you went through mud or then through a big tar pit, right? You slow down more and more as you go through something that's more sticky to you. In the case of light, if it's more dense, it's more sticky. It's going to slow it down more. And what that looks like to you is a change in direction of where it's coming from. So imagine there's a light somewhere in this room that bounces into the water, bounces off that straw and into your eyes, right? It literally takes more time to pass from the straw to your eyes than it does from here. And because of that, it looks like it's coming from another direction, right? If it takes longer to go from here to here than it does to go from here to here into your eyes, bouncing off of here, then it's literally just going to come off of his at a different angle. It's just weird. It's how light is. But what you should know is the more dense that medium is, the more the index of refraction is. So it's going to bend it even more, to the point that it could actually look like it's completely bent. Even though it's the same exact straw, this must be a much, much more dense liquid. Can you take a stop and think for a second? How does that explain why we have rainbows? Okay, so if you've ever seen a prism before, rainbows and prisms work exactly the same way, except for rainbows, the thing that's a prism is water droplets up in the sky. That's why it usually happens after rain, right? So light comes into whatever it is, this thing of a different density, and it changes the direction. And on the way out, a lot of times because of the shape of it, it will cause it also to reflect in an even different direction. But notice, remember that purple light is much more energetic than red light because it has a shorter wavelength. It's more likely to interact with whatever it's going through, so it slows down more. It changes direction more, which isn't a big deal here. You wouldn't really see a rainbow right here, but the further and further out it goes, it creates some distance between those different wavelengths of light, which is what we see when we see a rainbow. Or if you've ever seen a prism casting a spectrum onto the floor or wall of your room. This is all due to refraction. So once again, you might even see like people talking about fish in the water. They might look like they're in one spot, but really be in another altogether. It's because as that light bounces off the fish and up to the water, at the point where it crosses over the water air barrier right here, it changes direction again. So where it really is down here compared to where it looks like it is up here. Okay, I'm going to stop the video here, and then in the next video we'll talk about reflection, which is the one we're most used to, because y'all look at yourself in the mirror. Don't deny it.